Okay, hello everyone. This is Dr. Gallenstein, and today we'll do a short lecture on optimization. All right, so today we're going to talk about optimization. Optimization is a very important economic tool, or mathematical tool, I should say, for the study of economics. The reason why it's so important is because, as we spoke about in class, we are assuming that agents behave rationally, or they behave according to rational choice theory. And according to rational choice theory, people have well-defined preferences, and they make decisions to achieve as much of what they prefer, given as they can, given their constraints. They make decisions to optimize or to maximize, as we would say, their utility. And so if we want to translate that rational choice theory into mathematics, we need to have some mathematical tools that will allow us to optimize. This will give us the ability to study individual decision making. So let me explain briefly the process of optimization. That's what we'll do in today's lecture. Okay, so allow me to just explore a function f of x. So f of x, like I said, is a function. It takes x as an input, and then it gives some output value, f of x. I will just graph it here. I'm just going to kind of make up a function that will be helpful for us. So we have x on the x-axis, f of x on the y, and let's say the function looks something like this. If we have a function like this, then we can just look at it. If I said, okay, well, where's the optimal where's the maximal value of f of x? What is the highest amount of f of x? Well, that's pretty straightforward. It's going to be somewhere around here. This value right here is the highest value that f of x will achieve. Okay, and f of x achieves that highest value, that maximum value, at some value x that we will call x star. All right, so f of x star is the largest value of the function f of x. X star is the value of x that maximizes, so x star maximizes the function f of x. All right, x star maximizes the function f of x. X star is the value of x that gives us the highest amount of f of x. What we want to do in today's lecture is we want to figure out how do we find x star. This is going to be very important. We're going to do it all the time in class. We're going to use this method called optimization to allow us to find the x star of some function. Why would we do that? We do that because we want to study people's decision making. We want to study decision making. And according to rational choice theory, people make decisions, people choose to maximize their utility. Okay, so kind of predicting what's coming, what we're going to eventually have is we're going to have a function that is a utility function. And that utility function is going to be a function of some good. Let's say it's coffee, or C. So if we wanted to know how much coffee are people going to consume, well, we want to know C star. We want to know how many cups of coffee would someone consume such that they achieve the highest amount of utility. So we want to know the C star, the number of cups of coffee that maximizes utility. Okay, so if we were to actually write out a utility function of coffee, that means how much subjective value people get from coffee, we could then solve it to find the number of cups of coffee that they would need to drink to achieve that maximum utility. And if we find the number of cups of coffee that they would need to drink to achieve the that they would need to drink to achieve the highest amount of utility, then that would mean that this level of coffee is the number of cups that they choose. So that means that they would choose C star. All right. So that's just maybe kind of getting ahead of ourselves, but allow us to predict it. It will allow us to predict why we need to know this. Okay, so there we go. That's the background. That's what we want to do. Let me just save this in case you want it, and then we'll move on. And so we're going to do, oops. Optimization. 1. Okay, so let's just save that. All right, so that's what we're going to do today. We want to find how to optimize a function. So let's talk about it. How do we optimize a function? Well, for us to get a handle on how we do this, let's again draw our function. Okay, and we reach this maximal point here. All right. Okay, and now if we want to know, if we want to find, let's say we want to find X star. That's what we want to know. We want to know what X star is. That's our ultimate goal. What is X star? That's our goal. Okay, well, let's just do a little bit of review that will give us the resources we need to find X star. All right, so first, let's review. What does, and let's review by me first asking a question. What does the derivative of f of x, so f prime of x, the derivative, we also can write it derivative of f with respect to x, okay? What does this tell us about the function f of x? What does f prime of x, what does the derivative tell us about the function f of x? Well, if you remember, it gives us the slope at x. So f of x gives us the slope, let's expand this, slope of f of x at any point x. Okay, so let's just review that. Let's say I had some value x1, all right. So this at x1, this is f of x1. Let's make this a more pronounced 1, okay? All right, so it's f of x1. Now the derivative, let's do this. The derivative of f at x1 is going to give us the slope. So the derivative is going to give us the slope. I'll represent by this tangent line. The derivative is going to give us the slope at x1. So we could say here that the slope will be positive at x1. It's sloping upwards. Okay, now what if I had, let's say here, let's call this x2. Again, what does the derivative tell us? The derivative at x2 is going to give us the slope of the function at x2. So what is the slope of the function at x2? Well, we don't have the exact number, but we know the sign, and it's going to be negative. Okay. In light of knowing that, we can use that information to as a tool to be able to identify what the optimal point is. So let's think about how that would work. So let's say we start here from x1 and we move our way up towards x star. So we move our way up. As we move up, we know that the slope is still positive. It's still positive. It's still positive. That's less positive, but it's still positive. And then we reach something very interesting here at this maximum point. Remember, here's our maximum point. And we'll notice something very interesting at this maximum point. What is the slope at the maximum point? What's the slope here? The slope here is 0. What does that mean? That means that the derivative of f of x at x star is equal to 0. All right, the slope is 0 means the derivative at x star is 0. All right, if we keep moving beyond it, the slope starts to become negative. This is an incredibly important observation right here. The function has a maximum when the derivative equals 0. We can take advantage of that as a tool to help us figure out what x star is. All right, so, all right, the max value of f of x is at the point where f prime of x is equal to 0. All right, so here's a really important point. This is where the function f of x reaches its maximum, when at the point at which f prime of x equals 0. That means that x star is the value of x where the derivative of f of x equals 0. All right, this is the critical point here that I want to point out. We're going to use this observation to figure out how to find f star, or I'm sorry, x star. So the value of x that maximizes the function. All right, so let's take that insight and let's formalize it into a set of steps as to how we would find the maximum. Okay. All right, so let's formalize it into some steps. Steps to optimize. All right, steps to optimize. Step 1. And maybe I'll draw the graph over here just to remind us. Oops. Okay. All right, step 1. Find f prime of x. All right, so we take our function f of x and we take the derivative, so we find f prime of x. Step 2 is we set f prime of x equal to 0. As a side note, this is called the first order condition. First order condition, or the FOC. All right, so we take our function, we take f of x, and we find f prime of x. Then we set f prime of x equal to 0. We know that the optimal value of x is the value of x where f prime of x equals 0. So step 3 is solve f prime of x equals 0 for x. Solve this function for x. And the solution, the value of x that you find, will be x star. This is the optimal value. Optimal value of x. This is the value of x star. This is the value of x at which point the function reaches its maximum. All right, so that is the steps to doing maximization. Okay. One more caveat. Let me point a couple. Let's see. One quick additional caveat. So let me draw two functions. All right, here's a function. Has a maximum value here x star, okay. Then here's another function. Let's call it g of x. And it's shaped like this. And it has a minimum value here. Okay, now, what is the slope at this point? Well, we know that f prime of x equals 0. But then now let me ask you this question. What is the slope here? Here we know that g prime of x equals 0. Well, now we have a bit of a problem. I mentioned before that f prime of x equals 0 at the maximum. But just because the derivative equals 0 does not mean necessarily that that is a maximum point, because it also could be a minimum point. Here, the derivative of the function equals 0, but it's not a maximum, it's a minimum. It's a minimum value. So now we have a bit of a problem. This is a max. This is a min. A minimum value, this is a maximum value, this is a minimum value. But you can see that just because the derivative equals 0 doesn't mean it has to be a maximum. If the derivative equals 0, it could also be a minimum. So how would we distinguish between a maximum and a minimum? Well, let's do another bit of review. Can anyone remember what the second derivative of a function tells us about the function? What does the second derivative tell us? Second derivative tells us the curvature. The second derivative tells us the curvature of the function. If the second derivative is positive, then it will be convex. If the second derivative is negative, it will be concave. So, building on that, let me ask you this question. What is the second derivative of f of x at x star? Is it positive or negative? You'll remember it's negative. This implies, choose a different number here, concave. All right. What is the second derivative of g of x at x star? Well, it's positive. That implies convex. Okay, so if we want, if this first order condition, that is when the derivative equals 0, if we want to find a maximum, that means that the function needs to be concave. So maximum goes with being concave. If we want it to be a minimum, that means the function needs to be convex. So you see this is a concave function, it's faced downwards. This is a convex function, it's faced upwards. And so if we're finding a maximum, that means the function will be concave. If we're finding a minimum, that means the function will be convex. Okay, and so if you do not know the curvature of the function in advance, then you can solve for x star. But then for you to confirm that it's a maximum and not a minimum, you need to confirm that the second derivative of the function is negative. That would imply that the function is concave, which means that the value that you have found is a maximum value and not a minimum value. In some cases in this class, we will want to find maximum values. In other cases in this class, we will want to find minimum values. We know the difference. We know whether what we found is a maximum or a minimum by looking at the curvature of the function. If it's concave, then we found a maximum. If it's convex, then we found a minimum. Okay, thank you very much, and I hope you have a great day. In the next lecture, we will look at constrained optimization.